Hi friends, welcome to this brand new video on bibliometric analysis with Biblioshiny made easy. So Bibliometrix is an open source R package that provides tools for comprehensive bibliometric analysis. Biblioshiny is its web-based graphical interface that allows users to perform these analyses interactively without writing any R code. Let's see bibliometric analysis made easy with Biblioshiny in this video. So bibliometric analysis is a quantitative research method used to analyze scientific literature and academic output. It measures patterns, trends, and the structure of publications using statistical and mathematical tools. By examining metadata such as authors, titles, citations, keywords, journals, and collaborations, bibliometric analysis helps identify the influence, growth, and interconnectedness of research in a given field. These are the key units of bibliometric analysis: the documents, articles, conference papers, books, authors, individual or collective research output, sources, journals or proceedings, institutions and countries, which includes universities or countries, keywords and topics, emerging or dominant themes. So it works on the following sources: Scopus and Web of Science, most comprehensive for peer-reviewed journals, especially valuable for AI and journalism, which we will be demonstrating today. Then there is Dimensions and Open Alex. So there is Dimensions, which provides a very comprehensive database, and Open Alex is absolutely free. So these are the applications of bibliometric analysis. It maps research trends and growth. It evaluates research performance. It informs strategic decision making. It supports systematic literature reviews. It spots collaboration opportunities. It supports bibliographic and library services. And it enhances institutional and national visibility. So the first step in bibliometric analysis is to define the research objective. It begins with framing a precise research question, and then identifying the scope, the time frame, the subject area, and purpose, whether we are talking about trend analysis or influential authors. Then we select the suitable databases. It could be, as we said, Scopus, Web of Science, Dimensions, Open Alex, or even Google Scholar. The third step is about constructing the search strategy. We might need to use Boolean operators and or not, or combine keywords with controlled vocabulary. We then need to export the data in formats like BibTeX, CSV, or RIS. And we need to include all the fields such as title, abstract, authors, affiliation, keywords, cited references. The fifth step is about data cleaning and pre-processing. So we need to remove the duplicates, standardize author names and affiliations, normalize keywords and journal names, and fill in missing values where necessary. At times we might need to combine databases as well. Then we need to choose the type of analysis, whether we talk about performance analysis, which is productivity and citation metrics, or science mapping, which is co-authorship, co-citation, bibliographic coupling, or covert analysis. We then perform the analysis. Bibliometric or Biblioshiny provides lots of indicators, including publication trends, H-index, citation burst, thematic evolution, etc. We then need to visualize the findings, which is about creating maps, collaboration networks, keyword co-occurrence, citation landscapes. We interpret the results, we link the finding to domain knowledge, and we report and present. So this is the Biblioshiny workflow. We will begin with the main information, an overview of the documents, the sources, authors, documents, clustering, conceptual structure, intellectual structure, social structure, and we download the report as well. I will first demonstrate downloading the dataset from Web of Science. Generally, all institutions have a Web of Science subscription. You just need to log in from your university ID or from your university IP address and go to Web of Science. And this is the interface. Just go to the field and type in Artificial Intelligence in Journalism for the document search. You need to click in all fields here. and that will lead you to this page containing all the documents in artificial intelligence in journalism. We'll now need to export these files as BibTeX files, and we will need, in the record content drop down box, I'll need full record and cited references. So there is a limit there. I can only download 500 documents when I check in full report and full record and cited references. So I'll have to do it in 2 tranches. So let's download 1 to 500 first, and that will be downloaded as a BibTeX file because that's what I've selected. Now once that is downloaded, it's there on my downloaded folder. I need to go back and go for the remaining 45, from 501 to 545. So that's all. These are there as 2 BibTeX documents. Later in the video I'll tell you how to combine these 2 files, but as of now I have downloaded all the 545 documents, the full records and citations from Web of Science. So before we start using Bibliometric and Biblioshiny, we need to download R first and then RStudio. So this is where we download R from. We go to the CRAN and we need to download this R 4.5, and we need to install it first. So let's install R on our system. So just accept the default. So R is getting installed onto my system. So R has now been installed. Once R has been installed, we need to look at RStudio. So we need to go to RStudio for Windows and we will install the RStudio desktop. So we will download this RStudio desktop for Windows. It's a 281.27 MB file as we can see, and then we will start installing that onto our system. So here's RStudio. Let's install it. So it will take some time, so let's wait. So we've installed RStudio. Now we'll open RStudio. So this is important. They will ask you whether to use the default version of R. So that's the default version and we'll keep it. Just click on OK. So here we have the R interface. So there are 2 ways in which we can install a bibliometric package here. One is we go to the script here and we type install. As you can see, there's a drop down menu, install packages, and just type the first few letters, biblio. As you can see, it will show in the drop down. The other way is to go to install here on this particular part of the R interface. As you can see, there are files, plots, packages. So you click on to packages and then you go to install, and here you just need to type in, drop down is there, the drop down list is there. Just click on to bibliometric. This is important, install dependencies, and just install. So either we can type it there and run from there, we can even type it down there in the console, or we can do it through here. So I'm just showing it through this drop down list, which is the easiest one, and just install. So as you can see that this is being installed here in this window. Let me just take this up for you. So all these dependencies will be installed here, and as I told you, this installation will take, or this is required only for the first time. And as you can see, this is just a very simple process. The RStudio takes care of everything. So now it has been installed there. If you come and look here, you can see that it's there. We can see Bibliometrix is there. So every time we are using it, if I shut it down and use it again, I'll need to add it to the library. So either I can give the command library and I'll click on to library, and then again I type in biblio. It's there. If I run it, it will be added to the library. The easiest way is just by clicking this. So if I just check this box bibliometric, it will be automatically added to the library here. As you can see that it's added to the library. To start bibliometric, we first of all need to add bibliometric here, and then we just need to digit Biblioshiny. So we can just copy it from here. So let me just put it here, run it, and it will open up into the browser window. So this is the bibliometric interface which is being opened up in the browser window. So it takes some time to load up for the first time. And here we are onto the bibliometric interface. So we will do the bibliometric analysis on this interface. There are 545 documents that have been extracted from Web of Science, and they are in 2 different files. So we need to combine them, and an easy way to combine them without using code is through Notepad++. And once you've installed that, we need to work on combining them. So I'll just show you how to combine them. So these are the 2 things that have been downloaded here. So these are the 2 files that we've downloaded from Web of Science. So the first one has 500 documents, the second one has 45. So let's open this with Notepad++. So I'll choose another app. So I'll open these files always with Notepad++. So I can see that this is the file that has been, the first one that has been downloaded. So all the information, it's up right there. So if I come down there, this is the last one. So immediately after that, on the next line, I'll open my second Web of Science file. I will select all. I will copy and add it to the first file. Right at the very end, I will paste it here. So all these files have been pasted here. Now I will save this as, I have to save it as a .bib file. So I'll name it wos.bib, and I will save it. So now these 544 documents are in one single file. So we will work on that on Bibliometric. So let's start analyzing now. So this is the interface, and these are the files that are supported by Bibliometric. As you can see, there's Web of Science, there's Scopus, there's OpenAlex, there's Dimensions. OpenAlex is a free and open source. You can download everything from there. There's Dimensions. So let's open the files that are required. Before that, if I go on to the info and if I look at supported files, this is a very important information here. The Web of Science, we can take documents in either the BibTeX format, in the plain text format, or in EndNote desktop format, and it exports all the metadata. The suggested format by them is plain text, but I wanted to show you by BibTeX. In Scopus, it allows these 2 formats, the BibTeX format and the CSV format. But the problem with the BibTeX format in Scopus is that it does not export the cited references. So for that we have to use the CSV format. So let's go to data, and this is where we import the data from import or load. And if you can see there, this is where the importing happens. So I'll choose raw files. You have to choose raw files because these are regarded as raw files. You have to choose the database. So the one that we're using is Web of Science. The others are there as well. So here's Web of Science. The author name format can be full name if available, or whatever and let's take our file. So if you remember, we had taken our file as WOS. I'll put a file there, and I will start importing it. And all the 545 documents have been imported here. Everything is there. The keywords 66 are missing. So this is the entire 545 documents in AI and journalism that has been imported here. So let's now get an overview of the document. Let's see the main information. So we start off with the main information, and here we can see we have documents from 1992 to 2025. There are 235 different sources, 545 documents as we saw, and some general information about that. If I want, this plus sign is very important there. If I want, I can add this to my report. So this has been added to the main report, which we will download at the very end. So this is where all the analysis happens. Now let's talk about the annual scientific production, and we can see that this is in a very neat plot. If you just see here, till 2016 there was hardly any document. In fact, there was no document on AI and journalism. So it started from about 2017 where we had 3 documents, and if you can see, it was a high of 2024. We can add it to the report, and we can also, if required, if you see there, we can just download it as a PNG file. If we need to, let's go back to this tab here and let's go for average citations per year. Commonly used indicator because it measures the annual scholarly impact of a publication, journal or author, and it normalizes citation performance over time so that there is a fair comparison. So it looks at per year. So per year in 2013 it was 0. Per year the average citations in 2014 it was 38.5. This is for all the documents, and 2017 it was less because in 2014 they were citing each other more. So average citation per year is a very important figure. So it's useful in trend analysis. Similarly, we can just add this one to the report as well. Let's go on to one of the most important things here in Biblioshiny, which is the 3-field plot. So we need to run this 3-field plot here. So let's run the analysis, and we get this wonderful 3-field plot here. So it starts on the left with the cited references. CR is the cited references. So for example, this is about one particular cited reference from Thurman in digital journalism. This is about author, and the right column is about keywords or descriptors. So the keywords are used is what we are trying to link on with. Similarly here, if you look at the first one, it's about Seth Lewis. Is 47 citations, if you can see here at the end of this. Incoming 18, so 18 incoming references, 10 outgoing, means there are 10 keywords that this author is talking about. So this is a beautiful kind of a link that a specific reference leads to the author, and it leads to the keywords or themes that the author's papers are associated with. So this features highly cited works. It speaks of the key authors. So all these are the key authors that have been identified here by name. These are the key research themes, the dominant keywords. So artificial intelligence, automated journalism, AI, human-machine interaction, ChatGPT, etc. These are these indicate the evolving topics, and these are the hotbeds of research activity. So if you're trying to understand who is publishing on what, which articles they rely on, and what research domains are growing, so this gives us a bird's eye view. It can help identifying the influential authors, the thematic focus areas, and the citation linkages that you can see. We can again add this to the report that we'll get at the end, and we can download this as well. And as you can understand, there's a lot of analysis that we can draw out from here. Now let's come to the sources. We can see all these here, the most relevant sources. So you need to run the most relevant sources here, and as you can see, the most relevant source here is digital journalism, which has 38 documents, New Media and Society, Professional Dahlia Information. So this gives us an idea about the important sources here. Again, as earlier, you can add this to the report. Then we have the most local cited sources. Now this is a term that we must understand. Local here means or 545 documents that have been cited here. So among them, the highest number of citations is from digital journalism here, telling us about within the boundaries of the data set, in fact the document that I imported from Web of Science, which journals or sources are cited mostly in these documents. So digital journalism is cited so many times across. Bradford's law. It illustrates the core sources in our data set. So it helps identify the small number of core journals. As you can see here, this is the core sources. The small number of core journals that contribute a disproportionately large number of articles on a subject. So these are the core sources here. So on the x-axis we have the source log rank, and here the number of articles. So the most productive one is on the left, which has about 38 documents. And we have another one here. As you can see here, Applied Sciences Basel, 6 documents. So that's an important area, or it also helps people identify where to publish and what to read, or it helps libraries prioritize journal subscriptions, etc. Let's come on to sources local impact. Again, as earlier, we have to run it. So the local impact here is measured by the H factor. The H index of digital journalism is 14. So this basically means is that the journal has 14 articles, each of which has been cited at least 14 times within the data set. So all these are the big impact journals here: digital journalism, computers and human behavior, new media and society, journalism practice, and as earlier we can get them in a tabular format. Let's go on to the next analysis here, which is sources production over time. Sources production over time. Again, let's run it. So the digital journalism, how it has grown over the years. In 2025 there are already 38 documents, similarly for other journals as well. As earlier, we can add it to the report. So the other thing is about the authors. So we've done it about the sources. The next thing is about the authors. So which are the most relevant authors? So let's click on the most relevant authors and let's run the analysis. So these are the authors. Zhang Y has 14 documents here. Chen Y has 12. Li has 12. So this is all about the important authors. Let's see the most local cited authors here. So let's run this again. Lewis has 85 local citations here, followed by Guzman al. We can also go for authors production over time. So over time, how they have performed. So this particular author, Li S, has been very active from 2006 to 2024. Similarly, so for example, this author Zhang has 6 articles in 2023. So the intensity of the circle here is about the number of articles. So here they have 4. So over time, and we can get it in a tabular form. Let's now see the other analysis. The Lotka's law. So Lotka's law is a bibliometric principle that describes the frequency distribution of scientific productivity. It states that the number of authors publishing n papers is proportional to 1 divided by n squared of those publishing 1 paper. So here we have the number of documents on the x-axis, and here we have the percentage of authors having written that document. So about 80% of the authors have only 1 article, and if you come here to this very end, only 0.1% of the authors have 10 articles. About 1% of the authors have 5 articles, and 12% of the authors have 2 articles. So generally most authors publish only 1 paper here. So here we can get a description of the number of articles and the percentage of authors. So this long tail suggests that people publishing more than 1 paper is very, very less. So let's go on to the author's local impact. Again, the same H measure. So Zhang has an H value of 8 here, suggesting that 8 of his articles had at least 8 citations. He tells us the most influential authors in this field. Let's go on to the relevant affiliations and let's run this. So this talks about which universities have the highest publication. So the Sung Kyun Kwan University has 60 articles. The University of Florida has 50 articles. The Tsinghua University has 48 articles. The University of Southern California 43. Fudan University 33. So there are quite a few Chinese universities, as you can see here. Let's see affiliations production over time. So over time, which universities, as you can see, the Tsinghua University has had the highest number of publications in 60, tells us how the universities have performed over the years. Let's see corresponding authors countries now. Let's run it. So MCP here stands for multiple country publications. So the paper involves international collaborations. So if you see here for China, MCP is 52. There were multiple country collaborations, while for 129 documents it was only single country publication. That means the paper's authors were all from China. Similarly, USA, there are 20 documents on which there is international collaboration. The rest of it is from inside USA. So this is a very important chart. It tells us about the global productivity. So India, 4 are from multiple countries, only 2 from Indian. So Indian authors collaborate more with outside authors. So if you're looking to initiate collaborations, we can look for countries which have high MCP, multiple country publications. Let's come on to the other affiliations. So countries, scientific production. So this is a diagram of where you can get, China has 903 documents, India 35. Countries production over the times also we can get here. So over time, how we've seen that it's grown with China. It has grown over the last few years in a big way. Most cited countries, as we can see here, China has the highest citations compared to USA, where the number of citations is lesser. So these are the 3 most highly cited countries. Similarly, we have the most local cited documents. We have most local cited references. So which are the ones which have been locally most cited? So this article by Carlson in Digital Journalism in 2015 has been cited the most number of times. So this gives us a comparative idea about how certain works have performed better. Another thing that we can see here is the reference spectroscopy. So it tells us the historically influential years in the scientific development of a field by analyzing the publication years of cited references in the dataset. So the seminal year, as we can see here, the seminal year is 2020. So this is the publication year of the cited reference, not just the documents. So we have the cited references, as you can see here on the y-axis, and here this is the year. But between this 2013 to 2018, this is the key, most heavily cited foundational references. So this tells us the intellectual kind of earthquakes, moments when research papers laid foundation for the current work. So it helps us dig into the past and find kind of intellectual ancestors for today's studies. Similarly, another very important thing here we can work on is the most frequent words. So these are the key words: artificial intelligence, media, news, journalism. The most frequent words that we can see here. We can also see that in a word cloud format. So just run it and we can get this in a word cloud format, in a neat word cloud format. We can also have a tree map here. Words are the keywords plus. Now we will go on to the clustering. So let's go by clustering by coupling. So this tells us, so this is about impact and this is about centrality. The green cluster we can see here is about communication, artificial intelligence, credibility. So this is where the centrality is in a midpoint, the impact is high. Here the centrality is high and the impact is at an average level, and here the centrality and the impact both are less. We can go for this thematic map, and that's very important. So this represents a thematic map which categorizes word clusters based on their centrality and density. So if we see this one, this is high centrality and high density. So they are well developed and central themes in the field, this one. So they are like the hot mature topics and all. So these are again important themes here, but with low density. So they're important but still under development or broadly constructed themes. If you see this one, this is low centrality but high density. They are well developed but isolated themes, and here they are either declining or they are newer themes. Biblioshiny gives me a very important idea about which are the ones which are doing well, which are the ones which are declining, which are the ones which are important but isolated, and which are the ones which are important but still under development. Factorial analysis, in fact. So similarly, this is based on correspondence analysis or multiple correspondence analysis. So these important terms, they give us an idea about the field as well. In future videos, I'll talk more about these. Similarly, in the collaboration network, we get to see how they've collaborated amongst each other. So there are certain which are, as we can see, isolated amongst each other. The others, there's more kind of interaction between them. So there are these wonderful collaborations, as we can see there. Even the country's collaboration is one analysis here. So as you can see here, there are so many things that you can do with map format. Finally, you can download. So these were the ones which were selected. We can export this to the report. So among the limitations of bibliometric analysis is it often excludes non-English and regional works, relies on citation counts that may not reflect quality, and lacks contextual depth. Data inconsistencies, self-citations, and name ambiguities can reduce accuracy, while its metrics can reinforce existing academic hierarchies and overlook broader impact.